So today we are going to speak about a new topic with respect to the previous ones, which is essentially the mechanisms that are responsible for accelerating elementary particles to very high energies. And in particular, we'll see, this is a very complex topic, but we will see the very basics, which are very important nonetheless. These are called Fermi mechanisms of second order, or either of second order or first order. We will see why they are called this way. Essentially, they work in a different way, but as a matter of fact, the first order is more effective, works better in accelerating, can explain a lot much better. And the first one is also called diffusive shock acceleration because it happens within shocks. So something that we already somehow got familiar with. And so, okay, so why are we interested in exploring the mechanisms responsible? Well, first of all, because we do observe high energy particles, which are extremely energetic, in particular so-called cosmic rays, particles that we observe just crossing the Earth, just crossing the atmosphere all the time. They can be as energetic as 10 to 20 electron volt. This is really mind-boggling energy if you think that this is the energy of one single elementary particle. And if you work out, for example, the kinetic energy of a macroscopic object, like, for example, a tennis ball, whatever you like, you see that the kinetic energy of a macroscopic object can be comparable with this kind of energies. So this is really impressive. So the question is, what is out there in the universe capable of accelerating particles to such high energies? So that's the question we essentially want to tackle. The first who thought out and just wondered and explored this was Enrico Fermi, kind of 70 years ago. And he just came up with this mechanisms, as we will see. Essentially, the ingredients, as you just consider, just wandering clouds with some entrained magnetic field, which kind of works as a mirror. So wandering mirrors, which can scatter the particles, and just working out the average effect on just random particles, we will see that there is a net gain energy by the particle. We will also see, as I said, another mechanisms which instead takes place within the shocks. So I will make also a few examples of typical astrophysical objects which are in which we find naturally shocks, both relativistic and Newtonian, non-relativistics. And we will see, as a matter of fact, that with these objects, the energy gain on average is significantly larger. So first order. First order in what? Well, we will see what is the relevant quantity. An example of this are the shocks that are developed in supernovae, something that I will be addressing more in detail in the optional course on multi-messenger astrophysics. But nevertheless, you are supposed to know what supernovae are, but essentially these are massive stars which are crossed by a shock wave which disrupts all the outer layers. So these layers then they move in the interstellar medium and then develop. There are two shocks which develop, but then nevertheless, so there are shocks which develop, and we will see that indeed with these shocks, so the shocks that are supposed to take place in supernova ejecta, so material which has been ejected during the supernova explosion, can explain particles with energies up to 10 to more or less 17 electron volts. The extreme of the extreme is given by gamma ray bursts, which are ultra-relativistic jets, which develop within some kind of massive stars. Not all the massive stars that go supernova develop this ultra-relativistic jets. Just a tiny fraction of them. And if you ask me which in particular, I don't know. We don't know yet exactly. We have a rough idea of what the ingredients required to develop an ultra-relativistic jet are, but essentially this is an open issue in astrophysics. So nevertheless, we do observe them. And in particular, we know that they develop ultra-relativistic shocks. So again, in particular, in this case, they are suspected to be responsible for the acceleration of some of the extreme cosmic rays. So I'm talking about cosmic rays. So let's have a look at the energy spectrum. So number of particles per unit energy. So in particular, what I, in principle, should show you is the dN over dE. So the differential number of particles per energy interval. This is slightly different. This is E squared. So it's sometimes called the nu F nu. So what are they? So essentially the dN over dE is the differential number spectrum. So how many cosmic rays you have per square meter, per second, per steradian, per unit energy interval. E square is just a way of calculating how much energy overall due to cosmic rays lies in a given energy interval. So and then you see a lot of, well, here on the right side you see the names of all the different experiments that provide these data, and also some names of the particles. So antiproton, proton here, electron and positrons. So a lot of things. So you immediately see that, for example, if you look at protons, you see that well, the rest energy is around 1 GeV. So you see that these are particles which are extremely energetic. There are not just protons, also some nuclei. And as I said, okay, so the scale you see up to 10 to 12 GeV, well, 10 to 11, I should say, GeV, the most energetic particles yet observed, and which means indeed 10 to 20 electron volt. This is a similar plot. You see the units of measure are essentially the same. And the only difference here is that you might see also the origin of which cosmic rays. So in particular, this black line is due to galactic particles, so particles which live and get accelerated within our own galaxy, while the kind of pink one, so which is dominating at the very high energy tail of the distribution, well, these have an extragalactic origin. And just to let you appreciate, just to make a comparison, so of the ability of natural accelerators, particle accelerators out in the universe, which are responsible, of course, for this, for the cosmic ray spectrum, and our ability in the lab to accelerate particles. Here are some of the most powerful particle accelerators. In particular, if you take the most powerful one, LHC here, you see that, of course, this is a log-log plot, so you see that LHC is orders of magnitude less powerful than what we have in nature. So this is just, if you think that you can study the most efficient way of accelerating an imaginary particle just by just taking LHC and ignoring everything just happening out in the universe, this is just ridiculous. So we are far from being capable of accelerating particles in the very way that some astrophysical objects do. So this is very important also to realize why some aspects of particle acceleration can only be addressed by studying the way these astrophysical beasts, let me say, work. So let's start our short journey through these mechanisms by starting from the less efficient one, which is the second order mechanisms. So what is this? Well, let's review the ingredients that we need to consider. We have a so-called cloud, which can be a ISM, stands for interstellar medium cloud. So let's suppose we have our galaxy, in which there are wandering clouds, and in these clouds just advect some, just carry on, transport some magnetic field which is entrained in the cloud. Okay, so let's suppose that we have a cloud with mass capital M here, and this cloud in the lab frame is moving with a velocity capital V here. Okay, is moving along the direction here, which I call the x-axis direction. Let's suppose that there's an elementary charged particle with a velocity v, not to be confused with capital V, which is the velocity of the cloud, which is traveling, and at some point it collides with this side of the cloud, and the angle between the two velocities is the angle here, theta, which I call theta. There we can think of essentially two qualitatively different possible collisions. The one which is called here in panel A, which I will be referring to as a head-on collision. Well, strictly head-on would imply that theta is 0. We consider head-on a collision where theta has a value which ranges between 0, so when it is this way, just colliding face-on, head-on, and theta, so between 0 and 90 degrees. Okay, so there is if you project the velocity of the particle along the x-axis, you see that there is a head-on collision. The opposite case, assuming that the particle is much faster than the cloud, of course the particle can also collide from following. So now it's kind of following the cloud. So in that case, theta would be greater than 90 degrees. Okay, so it would be an angle like this. Why it's important to distinguish them? Well, we will see in a moment. But essentially, in one case, we will see that in the lab frame, the particle gains energy. In the other case, just loses energy. Okay, so let's, of course, needless to say that with M, I mean the particle's mass, which is considered to be negligible, which makes sense with the cloud, with the mass cloud. Okay, so this is something. Let's work out, first of all, the probability for the particle of colliding with of making a head-on collision or a following collision. Well, what comes into play essentially is the relative velocity, if you think for a moment. In particular, given that we wonder how many collisions we have per unit time on average, considering, for example, the collision angle of theta, as I said here, what matters is the relative velocity. So in particular, from the point of view of the particle, if you project the velocity of the cloud onto the direction of the velocity of the particle, so you see that the relative velocity in this case is v plus v cos theta. This is just the relative. It should be minus because it's a relative velocity, but the velocity in this case, the projection of the velocity of the clouds onto this direction is negative, so that the cloud is approaching the particle. So this is just the relative velocity, easy to consider. While if we take theta in this case for a following collision as this angle, you realize that the particle is following the cloud. So by projecting the velocity of the cloud on this direction, you see that the cloud is moving away from the particle. So the relative velocity at which the cloud is moving away from the particle is just v minus v cos theta. So essentially, what I'm telling you is that the probability of a head-on collision for and we will see in a moment, assuming a random distribution for angles, and in principle there is no reason why, assuming, well, there is a preferred direction for the wandering clouds with respect to generic particles. And essentially, even considering moving to a mildly relativistic particle, not the cloud, so the cloud is still highly non-relativistic, so capital V over C is still negligible with respect to 1, it's a small quantity, but considering a mildly relativistic particle, so where V begins to approach the speed of light, not ultra-relativistic particle, it's still possible. Of course, the relative velocity is no more this one. You have to use a Lorentz transformation. In particular, the relative velocity is these guys over 1 plus minus v cos theta over c squared. But nevertheless, if you Taylor expand the relative velocity, also in the case of relativistic transformation, so Lorentz transformation for the velocity, you still see that as I said, expanding and keeping quantities up to first order in capital V over C, you have something like this. So I call here P as a function of theta as the probability of a collision as a function of theta in addition to a function of the velocity of the cloud. Where, as I said, the velocity here, the velocity of the particle doesn't show anymore because I assume a milder relativistic velocity. So I just replaced small v as more or less c. So essentially, now instead of considering distinguishing by hand, let me say, the two cases with a sign, I just include just plus cos theta, where cos theta now can vary from 0 to pi. So it includes both cases. So immediately see that, so for a following collision, cos theta is negative. So it means that essentially that even in this regime, head-on collisions are more likely than following collisions. And just to let you appreciate the intuitive aspect of this, it's from a qualitative point of view, is the same reason why, for example, when you travel along a motorway, or in the US, motorways are called highways, you encounter, you meet many more cars traveling the opposite direction with respect to the one that are traveling in the same direction of you. And exactly the difference in the number of cars per unit time that you cross, that you meet, just depends on on your velocity compared in that case to the average velocity of both flows. So essentially it's the same reason. Or why, for example, when you run during a rainy day, on average, you get much wetter in front rather than on your back. That's exactly the same reason, essentially. So you see that this is a very intuitive stuff. Now, let's work out, essentially, having established this different probability that we will exploit later on. Let's consider, so one single particle just colliding with one given theta angle with respect to that. In particular, let's consider the problem in one specific reference frame, which is the comoving frame of the cloud. Okay, so I call E before the energy of the particle in the lap frame prior to, so before scattering, before colliding. And I'm using, so Lorentz transformation to calculate what I call E prime, so the energy of the same particle now in the comoving frame of the cloud. Still, you see, I'm just using Lorentz transformation, so I'm still E prime is still the energy of the particle, just again before collision. Okay. So just Lorentz transformation, remembering that of course the energy momentum is a full vector. In particular, the energy transforms according to a time-like component. So this is just the time-like component of the Lorentz transformation. Considering, of course, that capital V, gamma V is the Lorentz factor of what? Well, the comoving frame is the comoving frame of the cloud. So here beta depends on capital V, so the velocity of the cloud, which is the velocity of the reference frame with respect to the lab frame. Okay, so we have to pay attention not to make confusion between what is the velocity of the cloud and the velocity of the particle. And P cos theta is the x component, because if you think for a moment, we are considering, as a matter of fact, a boost along x, because the x-axis is exactly the direction along which the cloud, so the comoving frame, is moving. And so P cos theta is essentially just the projection of the linear momentum of the particle along the x-axis, of course in the lab frame, or better, I should say minus P cos theta, because the particle is traveling from right to left. So here in the Lorentz transformation, you have minus V minus P cos theta, so minus minus plus, just like that. Now, let's do also the same for the way the linear momentum component along the x-axis transforms, again, according to Lorentz transformation. So this is just Lorentz transformation using, of course, the space-like component along, in particular, the space-like component parallel to the boost direction. So in particular, as I said, the x component of the linear momentum is minus P cos theta. So I have minus and minus here. Then I should have another minus should be V over capital V, because it's the velocity of the cloud, over C times E before over C. So minus minus, I collected one just minus in front of the bracket. So Px prime, what is this? Well, this is the linear momentum of the particle projected along the x-axis, still before collision. Okay, and I just calculate the corresponding energy and linear momentum along the x-axis now in the cloud comoving frame. Now, what happens through the collision? Well, this is an elastic collision, so the only thing that changes, E prime doesn't change. The energy is unchanged. But the only change is just that in order to conserve, to make sure that both energy and conservation and linear momentum are conserved, of course, the linear momentum, the x projection of the linear momentum just gets reflected. So it means that it changes signs. So if I call Px double prime the linear momentum of the particle in the comoving frame of the cloud after collision, this is just that it just changes sign with respect to the value that he had right before the collision. So it's just this guy with minus sign, so minus minus plus, just like that. So now we are interested in calculating the final energy of the particle in the lab frame. So now that we have the final energy and linear momentum after collision in the comoving frame of the cloud, it's just a matter of applying inverse Lorentz transformation, where here you have to put the energy of the particle in the comoving frame of the cloud. E prime didn't change, as I said, across the collision. And here the new component of the linear momentum along the x-axis, because the boost is along the x-axis. So what we call Px double prime. And plus, this plus is just because you're just applying inverse Lorentz transformation. So what was minus becomes plus. And I call this E after. So energy of the particle after collision in the lab frame. So by replacing what we obtained in the previous slide, you see that E prime is just E before plus VP cos theta times gamma V. But you have here an extra gamma V, so gamma V squared. While I also used the previous formula we got for Px double prime. So again, you had also a factor of gamma, which multiplied by gamma, again, gamma squared, and then this guy here. So there is just P cos theta plus V E before over C squared times V. So both are multiplied by V. Just like that. So you see, you recognize that there are two equal terms here, so they just get twice as large. So twice VP cos theta over E before. Well, here I simply collected E before. So if you collect E before, here you have 1. Here this is divided by this guy, and this is just V squared over C squared. So this is the total energy, the final energy of the particle after one scattering with the angle, when the scattering angle is just, where the collision angle is just theta. Now, you see here you have the ratio of the particle, of the linear momentum of the particle, so the magnitude of the linear momentum, P, over its energy. So if you can express as a function of the Lorentz factor and the velocity, you know very well that the P is just gamma mv, and the energy is gamma mc squared. So this ratio can also be expressed as the ratio between the velocity of the particle in the lab frame, of course, and c squared. So by replacing this into this, you see that in this term here, you have, instead of P over E, you have V over c squared. So capital V cos theta over c squared. So you see that all what you have inside brackets, between brackets, is just dimensionless terms, okay? So let's calculate the net energy change. So as a matter of fact, E after minus E before. Well, I told you that, okay, so this is just a way of calculating this guy. So when I just collected E before as this guy here, 1 over gamma squared, because I collected gamma squared. Very simple. Now, let's Taylor expand, in particular, given that capital V, everything related with capital V relates to the cloud. But the cloud, we said, we are considering non-relativistic clouds. So essentially, it means that gamma is slightly larger than 1. So in particular, if you Taylor expand it, you see that this can be written as 1 plus the first term is just V, capital V over C all squared. And this is a small number, of course, as long as the cloud is non-relativistic. And while here 1 over gamma squared, well, this is exactly 1 over gamma squared is exactly 1 minus beta squared, where beta is beta related to the cloud, not to the particle. So this is a minus, so instead of 1 minus, this ratio square is minus 1 plus. So essentially, you see that there's 1 here and minus 1 that just cancel out. And you have 2 here, and this guy also gain a factor of 2, so you can collect 2. Here, as I said, you can neglect this guy here. I could have simply said that gamma V can be approximately taken as just 1, given that, as I said, the cloud is non-relativistic. So essentially, you can also collect an extra factor of capital V over C. So in the end, the net energy gain is this guy here, times this term here. Now, you see that if you think for a moment, for any possible value of theta, it means that for an isotropic distribution of clouds, I mean, any possible direction between the velocity of the cloud and the velocity of the particle, you see that in the average, the expected value for an isotropic distribution of cos theta is 0, because it ranges, it has an even probability between -1 and 1. So you are left as a net gain of something which is V over C times V over C. So it's comparable. It's an effect which is it's an energy gain, relative energy gain, because if you calculate delta E over E, is comparable with V over C squared, and that is the origin of the name, second order effect, because the gain, the relative energy gain per collision is on average, as I said, comparable with V over C squared, and V over C is a small number. So it's bad from the point of view, or if you aim to accelerate the particle as efficiently as possible, of course, V over C squared is worse than V over C. So as I said, if we calculate by averaging and also taking particles which are mildly relativistic, well, you have to also weigh also by the probability, because I showed you before that the energy gain, here I just showed you that the relative energy gain also depends on cos theta. In particular, this is larger. This is comparable with V over C for when cos theta is larger than 1, then is a negative. Is a negative, so it's not a gain, it's a loss. When cos theta is below 1, is below 0, so it's negative. But on average, of course, you have to weigh. To weigh by what? Well, by the probability per unit time of having for the particle of undergo a given collision. And we saw that the probability also depends on theta. In particularly, head-on collision are more probable than a following collision. So by working out for any given particle, the average relative energy gain, so by relative I mean delta E over E. So by weighting the individual energy gain, which is this guy here, we calculated here, times well, this works for an angle around theta, so you have to weigh for the solid angle, so for how many particles, so how many clouds just satisfy this condition. So have an angle between, for example, within a given solid angle. So the sine theta, d theta is the elementary solid angle, but it should be also times 2 pi, but there is no azimuthal dependence, there's just a polar dependence. Times it is also weighted by the probability, as I was saying, since this has to take into account also that, as I said, head-on collision are more likely. In particular, by replacing all the values that we've seen, in particular the probability, as I showed you before, scales as 1 plus V, capital V over C cos theta, and sorry, okay, so and here delta E is this guy here, so where V over C, I put it here, 2, I put it here out of the interval, and just this guy here is, here I also exploited, as I said, that the small v, so the velocity of the particle is more or less c, so this term just becomes cos theta, which is here, and capital V over c is this guy here. Over, well, you have to, of course, to calculate, to normalize by the same term, except for the guy for which you're calculating the mean value. So, and of course, theta has to range between 0 and pi. So here I just copied the very same. And this is easy, but it's also instructive. So if you just work out a variable change, so you define by x cos theta. So you see that this is sine theta, d theta is nothing but dx, so d cos theta. So it becomes this guy here, and from 0 to pi becomes from 0. So from 1 to minus 1, and then you swap the two boundaries just because d cos theta is minus sine theta d theta. And here you work out all the, well, you have a product of these two terms. So you have four terms. This guy times this guy is x. So it means it's cos theta, so x. And then this guy times this guy is what I call here beta capital V. So beta capital V is nothing but capital V over C. And then you have this guy times this guy. So beta V times cos squared, so x squared. And then finally this guy times this guy, so beta squared x. Well, this is an integral between -1 and 1, so you can just neglect all the odd quantities. So this guy here and this guy here are giving you 0. So you're left with beta times 1 plus x squared. So very, very easy. So this is just for kids. I invite you to make sure that indeed this is nothing but 4 over 3 v over c, which multiplied by what you had here becomes 8/3 and v over c squared. So that's the proof of what I was saying. So that tells you on average, so you have a particle, mildly relativistic particle, which is wandering within in our own galaxy, for example. And the galaxy you think that is just filled up with wandering clouds, whose distribution is just isotropic. So there is no preferred direction along which all these clouds are traveling. So on average, the relative energy gain on average that the particle will have per single collision is, as I said, of the order is comparable of v over c. Well, v is a velocity which is much smaller than c, so it's not very effective. And this is indeed the mechanism. The Fermi, Enrico Fermi, as I was saying, was the guy who first carried out this calculation, and he just thought out of this possible way of explaining. So you see, essentially, this is interesting from several points of view. First of all, you have to consider that the magnetic field, if you consider the problem as we did in the collision in the moving frame of the particle. Well, in the moving frame of the particle, we exploited the elastic nature of the scattering. Why? Because you have just a magnetic field in the moving frame of the particle, of the cloud. Sorry, and you know very well that magnetic field cannot accelerate particles because of the Lorentz-Fold's nature. It's always perpendicular to the displacement, to the velocity of the particle. And indeed, in that frame, so in the cloud moving frame, in which you have just magnetic field, you have no particle acceleration, just a deflection. So how can, in the lab frame, can you explain from a qualitative point of view the fact that on average the particle does gain energy? Well, because if you look at the cloud from the lab point of view, a moving magnetic field, so a variable magnetic, a spatially variable magnetic field means also an electric field. And so that's the description that you are supposed to give to the phenomenon when you describe it from the lab point of view. So indeed, there are, from your point of view as an observer in the lab frame, you see also some electric field, which are what are, from your point of view, responsible for the particle acceleration on average. Okay, so that's the explanation why there is no contradiction. I mean, why from your point of view as an observer in the lab, you do see particles changing their energy, because you also see some electric field, which you don't see if you travel within the cloud, the generate magnetic the cloud. Okay, so this is an interesting comment, I think. As a matter of fact, is this mechanism, how effective is this mechanism? Well, there are some problems. And the first problem is that, as a matter of fact, if you consider practical cases, well, these clouds cannot have velocities which are far beyond 10 to minus 4 times the speed of light. So it means that the ratio of V, capital V over C, is typically as I said, kind of 10 to minus 4. The energy gain is 10 to minus 8, comparable to 10 to minus 8. And you might wonder, well, probably the energy gain per single collision is not exciting, but probably you have many collisions per unit time. But unfortunately, the mean free path for a typical case, you see, is not that small. So also the collision rate is not excessively high. So as a matter of fact, this doesn't look like a very promising mechanism. To explain, I remind you that in the end, what we have in mind is to find a mechanism which can explain what we observe. So not fancy ideas, exactly particles that we do observe every day. So this is not, in principle, it can work. As a matter of fact, it doesn't seem to be so effective. And if you rethink for a moment all the key passages of the proof that we just gave, what essentially is not helping is the fact that following collision essentially contribute to lessen the effect of head-on collision. So if there were a mechanism through which you can get rid of following collision, if there were a way to reject, to just remove following collision and just have head-on collision, then the effect, the energy gain would scale would be of the order of V over C, so first order mechanism. And we will see that in a moment that indeed shocks are something in which just first order effects, so just essentially head-on collision are what the particle just undergoes. And so this is one of the problems with the second order mechanism. Another problem is the so-called injection problem. Well, you know that particles just also can when you accelerate particles, you also have to account for ionization losses. So in particular, when you are through some media, particularly you have, and this curve here, the black curve shows you essentially how much energy is lost in this case because of ionization losses. So for example, something that can be described by the so-called beta block formula, if I remember correctly. And this also depends on the energy itself. So in particular, if we consider a mechanism which is through which the particle is gaining energy per unit time, so this is the E over dt, at a higher rate, so when the particle is starts from a very low energy, kinetic energy, of course. And you see that here at the beginning, this regime for very low energies, the rate, I'm looking at the blue line. So in this case, the rate at which the particle gains energy is larger than the rate at which it loses energy because of ionization losses. So in this case, it works. So what it depends on? What does it depend on? Well, it also depends on the kind of region. So how many particles, how many collisions of this kind can happen per unit time versus the rate of ionization that the particle is responsible for. While if the acceleration process just works like these lines here, well, in that case, you see that there is no way that you can reach up this, you can go in this regime. If you are in this regime, okay, at this point, what you gain is greater than what you lose. So the particle keeps on accelerating. But if you start from here, you see that here the rate of energy gain is smaller than the rate of energy loss. So in this case, there's no way you can go this way. So unless you go this way, or you find mechanisms that very quickly brings the particle from here to here. And so this is a problem, so-called injection problem. You have to immediately find a way to start with a particle which is already energetic enough to lie in this regime. Otherwise, there's no way you can. It's more what the particle loses rather than what the particle gains. So this is also another problem. And this is indeed an issue when you consider a mechanism like this one, which is not very fast, very effective in increasing the energy of the particle. So that's why the injection problem can be an issue when you have a mechanism which is not very fast and very effective in accelerating the particle. So another, as I was foretelling you, another mechanisms which in this sense is much more promising, and is the so-called diffusive shock acceleration. As we will see in a moment, this works as a first-order mechanisms. So there is a key idea which is very simple and can be thought of something, if you think of a ball which is bouncing back and forth between two screens. And these two screens there is a relative motion, so they are approaching. Well, it's just something for kids to show, or for first undergraduate students, to show that at every bounce, the particle gains energy. And you immediately see why, because they are all head-on collisions. In any case, they are all head-on collisions. You see, very beautiful. So, can we think of an analog mechanisms working for particles? Yes, and essentially that's exactly what happens across a shock. In a shock, we will see across the shock. So this is the region of the shock. Here you have the upstream fluid. This is the shock frame. So in the shock frame, you see the upstream fluid coming towards the shock, and then the downstream fluid, the shock fluid, just moving away from it. Well, if we consider, as I will show you in a moment, that on both sides of the shock, there is a magnetic field which is created by turbulence, and turbulence is something which is due to the shock itself. So the magnetic field, which is due to turbulence, works as the screen, the cloud that we saw in the previous case. So the particle is just bouncing back and forth between the two screens, the two magnetic fields. But there is also relative motion, because you see in the shock frame, you see that the fluids in which the magnetic field lives is moving. So you have a motion of these two screens. In particular, we know very well that there is also a relative velocity between the two fluids, the upstream fluid and the downstream fluids. So the relative velocity is such that they are just approaching. So the idea is essentially the same, where the screen here, the role of screen is played by the magnetic field due to turbulence, which develops on both sides of the shock, which makes sure that all these energetic particles just bounce back and forth. And by bouncing back and forth repeatedly, you see that the idea is just a sequence of head-on collisions. So you remove what was the biggest issue in the previous case. So following collision. Here you have no more following collisions. So that's a mechanism of the first order in V over C, where V in this case will be C in a moment, is essentially the relative velocity between the two fluids. But let's do things more properly. From an historic point of view, these studies, so while the second order Fermi mechanisms, as I was saying, was first introduced by Fermi kind of 70 years ago, people realized and just they began studying more in detail this diffusive shock acceleration. in the kind of 50 years ago, so in the 70s, I would say. So essentially, we can exploit what we derived when in the previous case. So the energy gain uh, across a collision is this guy here. Well, here the key idea, indeed, is that having to do with just head-on collision, essentially you make sure that cos theta is never negative. It can be different from, it's not necessarily one, but it is never negative. And so that immediately gives you, if we take again relativistic particles, so V over C is just one, you see that you have something of the order of capital V over C, so first order effect. So in particular, by considering exactly, precisely head-on collisions, of course, this is exactly twice V over C. Indeed, as I was saying, it is shown that, so this first order Fermi acceleration, so essentially the key idea I just illustrated in the previous slide, indeed can work, can take place, and indeed does take place in the presence of strong shocks, both non-relativistic, so the ones that we observe, for example, in supernovae, as well as, of course, relativistic shocks. So let's see more in detail. What happens? So let's give some names. Let's define some quantities. In particular, I call capital P the probability for a given particle to gain energy within one single scatter. And beta is the fractional energy gain, so delta E over E. Okay. So we wonder what happens to the particle after K scatterings. So the particle just underwent K consecutive scatterings. So you immediately see that if there is one probability for the particle to go through one single scatter, well, you are expected that the lucky particles that went through K scatterings, it means that they the probability, the corresponding probability for a particle to go through, to undergo K consecutive scattering is just P to the K. Let's call N0 as the starting number of particles. So in the end, how many of them will have undergone K scattering? Well, just multiply the initial number of particles times the corresponding probability for K scatterings. So N0 P to the K. And what's the energy of these particles? Well, the energy is just the initial energy multiplied by beta as many times as many scatters. So given that there have been K scatterings, so beta E0 has been increased. So you multiply every time by beta. So by beta times K. Now, if you work out a simple mathematical exercise, n over n0, and you calculate the logarithm of n over n0 is k times logarithm of p. You do the same here. So the logarithm of e over e0 is k logarithm of beta. You work out the ratio between the two. So here k and k just cancels out. So you're left with logarithm of p over logarithm of beta. So by inverting, again, you bring this guy on the other side, you take the exponential of both. So in the end, n over n0 is e over e0, and this is the index. So what is this? Well, this is the cumulative number of particles having a given energy. So starting from a population of particles with a population of n0 particles, all initially having energy E0. In the end, the distribution, the cumulative, why I say cumulative? Because particles which underwent K scattering not necessarily they have to stop there. Some of them will undergo no more scatterings, so in the end their energy will be E, but some of them could be even luckier and go on increasing their energy through further scattering. So it means that this number is the number of particles that have at least energy as large as E. If you want the differential distribution, so you want to know how many particles have energy, for example, between E and E plus the E, well, you have to calculate the derivative of this distribution with respect to E. Yes, indeed, as I said, this N is the number of particles having energy at least equal to E. At least. Some of them will stop accelerating, some of them will be even luckier and keep accelerating. So to work out, you have just to calculate the derivative. The derivative of a power law is really something for kids. It's just you gain an extra index of -1. So -1 plus this guy here. And this is the probability density distribution. So, or PDF, a probability density function. So what is telling me? Well, it is telling me that if I multiply NE, this function that now that I call NE, times the E, so this is the number of particles having energy between E and E plus the E. Okay, so this is a power law. This is interesting. So you start with a population of particles having the same energy, and you end up, thanks to those mechanisms. What is the key of this line of reasoning? Well, that the probability for each single scatter is the same, while energy increases according to a geometric distribution, because the relative energy gain is the same. So that's the reason. This is a very general argument in probability. It's our way of ending up with. Of course, this number is a decreasing distribution, and this makes sense because the higher the energy you want and the fewer the particles, because you are considering less and less probable events, the probability of having many scatterings. So let's focus more in detail what happens. So we consider something, we remind ourselves about what we considered at the time when we were considering shocks. So there are different reference frames that we have to keep in mind. In particular, there is the lab frame here, in which you have the unshocked fluid, okay, with the thermodynamic quantities, and capital U is the velocity of the shock with respect to the unshocked. So here the unshocked or upstream fluid, this is the shocked fluid or downstream. Okay, and this is in the lab frame. So this doesn't move, and this is moving, and the shock is moving with capital U velocity. In the shock rest frame, so the frame in which the shock is at rest, which is the one we consider when we derived both Rankine Hugoniot in the non-relativistic shocks, or the Taub condition in the relativistic shocks. Here we will consider non-relativistic shocks, okay, just for simplicity. So essentially the analog is Rankine Hugoniot solutions. So in here, of course, the upstream fluid is approaching the shock with a velocity which we call V1, and which is in magnitude, of course, the same velocity of the shock here. And here, V2 is the velocity at which the downstream fluid is just moving away from the shock. Here, 1/4 V1, I'll show you in a moment why. But this is just a consequence of Hugoniot, Rankine-Hugoniot solution. We will also consider two other frames. So the upstream fluid rest frame, so the frame in which the upstream fluid, so this guy, is at rest. Well, this is the same as this one here, is the lab frame, if you think for a moment. And then also the downstream fluid rest frame, so the frame in which it's now the downstream fluid which is at rest. Okay. So let's work out. Well, in the case of a strong shock, let's consider a monatomic gas. So where the adiabatic index, gamma, not to be confused, of course, with the Lorentz factor. This is just the adiabatic index. So for a strong shock, I should add adiabatic shock. I remind you that what we've seen at the time was a diabatic shock in which you neglect all radiative losses, so energy is conserved. So essentially, if you remember, one of the characteristics of the solution of the Rankine-Hugoniot conditions was the velocity, the ratio between the velocity of the fluids scales inversely as the ratio of the two densities, and in particular, in the strong shock case, it's just this ratio here, so which depends on the kind of gas you're considering. So 5/3 plus 1, 8/3 over 2/3. So this is just well, here here I just, so there is a typo, so it should be gamma minus 1 over gamma plus 1. So this ratio is indeed 1/4, but it is because gamma minus over gamma plus. Okay, so I will correct that. Sorry about that. So 1/4. So essentially, the velocity of the downstream fluid in the shock rest frame is 1/4 of V1, just because of Rankine-Hugoniot solution, something we are very familiar with. Very well. We can also calculate the relative velocities. Well, you know, both velocities in the same frame, which is the shock rest frame. So the relative velocity, which I call capital V, I define capital V as V1 minus V2. So the relative velocities. So it's just V1 minus V1 over 4, so 3/4 V1. But V1 is the velocity of the shock in the lap frame, so I can also call 3/4 capital U. So what is this? Well, this is the velocity. Whenever I consider one frame in which one of the two fluids is at rest, either in this case the upstream fluid, or in this case the downstream fluids, I see the other fluid which is approaching with a velocity which is the relative velocity. So 3/4 U, which is exactly what we calculated. So that should explain, should make you clear the reason why in both frames you see the other fluid approaching towards you with a 3/4 U. A key point is that now we have to pay attention. We have to make a clear distinction between, one thing is the particles which are thermally distributed. So the particle of the fluid, what we considered also at the time of when we analyzed the shocks, these are particles which belong to the Boltzmann distribution, okay? So which are of the Maxwellian distribution, the Maxwell-Boltzmann distribution. So thermal, let me call them thermal particles. So the particles whose average energy is of the order of kT, okay? And so the mean quadratic velocity is square root of kT over m, apart from the numerical coefficients. See, so these are the particles which are essentially built up the fluid. Here, we considered, in addition to these particles, we consider another population of particles which are relativistic particles, which is the particles we want to accelerate, and whose destiny is what we care of. We want to see what happens to these particles. So these particles are different. You have the population of thermal particle, and then a relatively small population of relativistic particles, which are the ones we aim to study. Okay, so this is important not to make confusion. Why is this important? Because these relativistic particles, which is what we care of, when they cross the shock, nothing changes for them. Because why? Well, I remind you that in typical astrophysical cases in particular, we are talking about collisionless shocks. So when the particles, whatever particle they are, they cross the shock, they do not collide with each other, but they essentially, because it is the magnetic field which acts in just randomizing their velocities and doing what happens. So essentially, and if you remember, in general, I told you, well, the width of the shock depends on the mean free path. It's comparable with the mean free path, which is, from a macroscopic description, is what makes the width of the shock negligible. because, of course, the macroscopic thermodynamic variables do not change significantly across a region whose length is comparable with the mean free path. But look, the shock wave is determined. So given that we are talking about collisionless shock, the only length above which a particle can change in the presence of the magnetic field can change its velocity is the Larmor radius. But look, so the shock wave is comparable comparable with the Larmor radius. But Larmor radius of what? Well, of the particles which are responsible for the fluid, which make up the fluid. So the thermal particle. But the thermal particles are highly non-relativistic. So it means that if you, on one side, consider the thermal particles, so the particles whose Larmor radius gives you the width of the shock, and the relativistic particle that we now want to consider, these relativistic particles have traveling essentially at the speed of light, much more energetic. So their corresponding Larmor radius is correspondingly larger. So it means that why the thermal particle, which make up the fluid, just crossing the shock, they change significantly their velocity, and we know exactly, on average, the amount of this change. Look at Rankine-Hugoniot solution. Well, the relativistic particle that we also consider living in this shock, their corresponding Larmor radius is much larger than the width of the shock. So, as a matter of fact, when these relativistic particles cross the shock, they do not feel anything, because to change you should take a much larger size than the width of the shock. So essentially, the big difference between the thermal particles making up the fluid and these tiny selected population of relativistic particles is that the relativistic particle crossing the shock, they do not even recognize. They are completely unaffected. But what happens then is so just across the shock, the relativistic particles just go unaffected. And then in the end, the magnetic screen provided by the magnetic turbulence that you have, then in the end they will randomize the particle, and they will send it back, the particle. So these energetic particles will cross the shock back and forth with the details that we'll see in a moment. But that's the point, why the thermal particles behave differently from these selected population of relativistic particles that are living through this shock. Because of that, okay? So let's consider more quantitatively what happens. In particular, let's consider particles crossing from upstream to downstream. So these are relativistic particles. So essentially, the relation between their energy and linear momentum is similar to that of a photon, this guy here. Let's give some names. Okay, let's call E the particle energy in the upstream fluid, so when it is here. So we are in this frame. In this frame, the energy particle is E. The particle energy is E. Let's call E prime the energy of the same particle as seen now in this frame. So the particle is here, is traveling towards the downstream fluid. So we wonder what during this travel we already, for what I just said, the particle just doesn't change energy by crossing the shock. So when we want to calculate now finally the energy of the particle that it has when it is here in the downstream fluid, it's just a matter of Lorentz transformation, nothing more, because the shock doesn't affect. So Lorentz transformation, okay, so what is this? Well, the particle is moving from here to here, so the linear momentum component projected along this axis is negative, so in minus p cos theta. Let's assume there is a cos theta angle. So minus minus plus px is p cos theta, where gamma v, capital V, I remind you, v is the relative velocity. So is the velocity I'm changing frame from here to here. So from the fluid, from the rest frame for the upstream fluid to the rest frame of the downstream fluid. So the relative velocity is 3/4 capital U, what I call just V. Capital V is this guy here. So Lorentz transformation, of course, gamma is the corresponding gamma. So, but what does this mean? Well, when the particle will be then just randomized as a direction, but not as linear momentum of energy, because the energy of the particle hasn't changed. It just changed. The function of the magnetic field that just lie behind the shock is just to randomize, just to change the direction of the particle, but not its modulus, the modulus of the linear momentum, I mean, so not the energy. So if you wonder, what's the energy change in the end? Energy change, I mean, between the energy that the particle has in this, evaluated in this frame, so in the upstream fluid rest frame, and the energy as evaluated in the downstream fluid when it is here and is ready to travel back. Well, this is E prime minus E, just like that. So delta A is this guy here. So the energy change of the particle as evaluated here when it was here in the upstream fluid rest frame, and then when it is here in the downstream fluid rest frame, if you compare the two energies, well, the two energies are different. And by how much? Delta E over E is of the order of V of C over cos theta. Now we have to calculate the rate, the probability for a given theta angle. Well, first of all, of course, you have to weigh by the solid angle. Of course, if you consider a small solid angle, you will have correspondingly fewer particles. And also by the rate at which you have particles crossing the shock. In particular, you have more particle when the cosine is larger is close to 1, and when the particles are close to almost parallel to the shock, you have correspondingly a lower rate of approach. And here too is just to normalize the probability to 1, of course, because here theta is what? Well, theta, you have to consider only particles. For example, if you look here, the upstream fluid frame, you only have to consider particles which are moving towards the shock. So it means that theta has to go from 0 to 90 degrees. We are focused on particles which do move towards the shock. So by calculating, so that's essentially the reason why shocks provide just head-on collisions, because you just got rid of, it's a sequence of head-on collision. So that's the real true difference, powerful difference with respect to the previous mechanism. So by calculating the average gain, so by weighting by the solid angle and by the in general by the probability I just said, and the single energy gain in just one crossing, so if I'm crossing from upstream to downstream. Well, this guy, well, okay, just replace here the value, this and this one here. So you see, just for kids, this is this guy. This integral is very easy to calculate. So this is just the derivative of cos cube, if you think for a moment. And with the due calculations, you see that you end up with, indeed, because of, you see, the real novelty is that you consider only positive values of cos theta, just head-on collisions. So that's why you are left in the end with a V over C. And now we have to consider, now the particle so far has gone from here to here. Now the energy change, now the particle is here, and the magnetic field due to turbulence here is now reflecting back to the particle. So the particle is ready to go back. But again, let's consider the problem. We have to go back with the particle from here, from the downstream, again, up to the upstream. But you see, the relative velocity now, the relative velocity at which the downstream fluid sees the upstream fluid approaching is the same. So the mechanism is exactly the same. So we gain an extra fact, we gain the same energy gain. So the net energy gain is then twice as large. Okay? For the very same reason, it's completely symmetric from this point of view. So from one cycle, where cycle it means, okay, you were here in the upstream, then you move here, and then you get screen, you bounce back, and you get here. So you cross the shock twice. So what's the net energy gain? Twice the sky. Very, very simple. Beautiful. Because this is a small quantity, I remind you, capital V, we are considering non-relativistic shocks, so V over C is small. But again, just using the previous notation, if you remember, I called beta as the energy increase, the relative energy increase in one single cycle. So let's consider, instead of one single scattering, one single cycle. So back and forth, okay? Back and forth once. So the overall energy gain is this guy here. So E over E0 is just 1 plus delta E over E. So this guy here. So this is beta. Now, let's consider more in detail one thing. There is only one thing which is not symmetric with respect between what happens in the upstream fluid rest frame and the downstream fluid rest frame, which is this guy here. If you consider from the point of view of the shock frame, in the shock rest frame, the upstream fluid is moving towards the shock, but the downstream fluid is moving away from the shock. So the fact that the downstream fluid is moving away from the shock, there is advecting, given that the screen, the magnetic screen, is addressed in each fluid frame, it means that here the screen, if you think of the magnetic screen as your previous cloud, the cloud is somehow moving away with respect to the shock, with respect to the shock. So it means that there are some particles which will get lost. They will not get back. So let's calculate more in detail this particle. So let's assume that n is the particle number density. What? Particle number density of the relativistic particles I have in mind, not the thermal one. Of course, the thermal particles are most of them and are there. That's what give us Hugonot, Rankine-Hugonot solutions and whatever. They are responsible for the pressure, temperature, density, everything. In addition to them, we have a tiny fraction of particles whose particle density I call n. Okay, so number of particles per unit volume. So how many of them, assuming an isotropic distribution, so let's consider the upstream fluid here. If I want to calculate how many of them will cross the shock, and given that they are moving randomly, they are relativistic particles, so their speed is essentially c. Well, I tell you that the number of particles crossing, so the flux of particles, the net flux of particles, so the number of particles crossing per unit time per unit surface, the shock is just this guy here. Why? Well, it's a matter of calculating the flux of an isotropic distributed population. So n is the total number of particles I have per unit volume, but I want to select only those moving somehow towards the shock. So if I consider n times d omega over 4 pi, I'm just taking all the part in a given volume element, per unit, in a unitary volume element, I'm considering only the particle moving within a given solid angle. So n times this guy is the number of particles, is the density of number of particles moving within a given solid angle, times the velocity. Density times velocity is the flux. And I want to multiply the net flux across this guy here. So I take the unit vector, which is perpendicular to this guy. I called x the line of motion here, so this is just I. So by multiplying all this, I immediately see that essentially what I come up, v times E gives me a cos theta if I consider a generic particle moving this way. So the angle with the projection gives a cos theta, and d omega gives a sine theta. So if we work out, assuming V as C, as I said, we are considering relativistic particles, we end up with this guy. So the factor of 1/4 just comes from that. If all the relativistic particles were moving parallel towards the shock, of course, they would be NV. But here, the particles, when they go through this magnetic field, they are just isotropically randomized. So just a fraction of them will move towards the shock. How many of them? 1/4. As I was saying, as a matter of fact, the fluid, the downstream fluid, with respect to the shock, with respect to the shock, has a velocity which is v2 and which is moving the other way. So in particular, in the downstream fluid, you see the shock which is moving away from you. In this frame, the downstream fluid is addressed. And if you live in here, so if you are a particle in here, you are randomized velocity. But you see the shock which is moving away. Well, the upstream fluid is moving towards you with this velocity, but the shock is kind of running away from you with a velocity which is v2, Rankine-Hugoniot solution. So as a matter of fact, the flux that gets lost is n, the number of your particles that you have in mind, which is the same, by the way, is the same between the two shocks. These relativistic particles have the same number density for the very same reason I told you before, because these particles, when cross the shock, unlike the thermal particle, they are unaffected, so their density just doesn't change. So n is the same for both sides. So number of particles per unit volume times v, because here v2 is the bulk velocity with respect to the shock, or if you want, the velocity of the shock in this frame. So this is the flux which is lost because of the advective motion of the downstream fluid with respect to the shock, or as I was saying in this frame, because of the shock is kind of running away from the fluid. And if you remember, V2 is capital U/4. So if you work out the ratio between what? Well, between the number of particles that are crossing the shock, so this guy here, 1/4 nc, and the flux of particle which gets lost, which cannot bounce back to the upstream fluid, but are just advected away because of the downstream fluid motion with respect to the shock, which is the numerator we just calculated. So this is the ratio, the fraction of particles which do not make it back. They get here and then get lost because of this motion. So this is, as a matter of fact, the fraction of particles that are lost by any time. They bounce here, but they do not make it back anymore. So from the point of view of one single particle, this is the probability for one particle of not making it back in one single cycle. But given that we call P the probability of making it through one cycle, well, you realize that P is 1 minus this guy. The probability of making equals the probability that 1 minus the probability of not making. So 1 minus U/C. See, here I have the logarithm, so the logarithm. But given that U, the velocity of the shock, we are considering non-relativistic shock, so this guy is much smaller than 1. So Taylor expand, this is more or less minus U/C. On the other side, we just calculated beta, So if you remember, the ratio between the two logarithms was what gives us the index of the particle energy distribution. So this guy is -1. But if you remember the differential distribution, which was what we cared of, so what I called in the previous, in the initial slide of the energy spectrum of the cosmic rays, I called dN over dE. I should have called dN over dE, but the important is to understand the meaning. So it was -1 plus this ratio, so -1, -1, -2. So indeed, we see that according to this mechanism, so to what happens, so to this bouncing back and forth across the shock of these relativistic particles, so indeed the final energy distribution that I am expected to see is a power distribution with an index of -2. And this essentially can explain, and indeed this is something that I didn't tell you, but indeed we see that the spectrum of these energetic particles, indeed there is an index, a power law index between 2 and 3. So clearly the proof that I just provided you with is an oversimplification. Then there are many aspects which we did not consider. But the essence, the very essence, is already caught by this line of reasoning. So that's why it's important. That's why we just went through that. And just a few final comments. We know, but that, as I was saying, the supernova remnants, so these ejector, this material which has been ejected at non-relativistic speed in the case of supernovae, or relativistic, ultra-relativistic speed in case of GRB shocks, are indeed the best place for something called diffusive shock acceleration. Diffusive because there is a diffusion process when the particle each time crosses the shock and enters the magnetic field the turbulent magnetic field region. Then there is also diffusive process, which is also the process by which the velocity of the particle gets randomized. And so what we observe, and now I recall your knowledge from what we've seen about radiative processes. You know that when you have energetic particles, in particular relativistic particles, you immediately know that the signature of these particles can be synchrotron radiation, for example. You are in the presence of magnetic field, in the presence of ultra-relativistic charged particles, so you have all the ingredients to expect this kind of phenomena. And indeed, we study the properties of the result of these acceleration processes also by studying the synchrotron radiation or inverse quantum radiation. So all kinds of radiation due to relativistic particles in these regions, in which we know that there is this kind of process. What is mostly researched is exactly the nature, the way these turbulent magnetic fields just are created. This is a very complex topics. And in particular, there is a mechanisms that you need to invoke, which is a so-called magnetic field amplification. So there is in this turbulence is, by the way, one of the most complicated topics in dynamics of fluids. And it is known, but it is very complex to study the way it works, that in the presence of this turbulent magnetic field, there are some mechanisms which are capable of greatly amplify the magnetic field. If you don't call for them, well, in that case, you cannot explain the extreme energies beyond GeV, for example, that we observe from protons. So indeed, these mechanisms, so the capability the need for some mechanism which can greatly amplify the magnetic fields that are created across shocks is really important. Otherwise, you cannot explain this. Yes, indeed, as I was saying, the observational evidence that indeed supernovae shocks, for example, are indeed places in which all this takes place is because we observe it from radio to X-rays, synchrotron radiation, and you know very well that when you measure synchrotron radiation, you can find a way to constrain, to measure, to estimate the energy of the electrons responsible for that. In that case, you see that you have extremely energetic electrons, so electrons whose energy can be 10 to 13 electron volt. So Lorentz factor, which is orders of magnitude greater than 1. And also in some cases when we have evidence for gamma rays due to the pion production. These pions are produced by protons which then collide, and which has to be, again, also protons, has to be extremely energetic, 10 to 100 up to 100 TeV. So it means 10 to 14 or 10 to 14 eV. So kind of 10 to 4, Lorentz factor 10 to 4, 10 to 5. And as I was saying, also, for example, we can obtain, you know very well, if you remember what we've seen about synchrotron radiation, and I told you, when you probably now remember that when I told you, oh, it's interesting to study the synchrotron radiation of a population of electrons where the energy distribution of the population of electrons is a power law. You remember that? And I told you, oh, we will see why it makes sense to consider a power law distribution of the energy of electrons. Now you see why. Because shocks are capable of building up these power law energy distributed population of electrons. Now you see why. And in particular, you remember that when you measure the index of the spectrum of synchrotron radiation from a population, S, what we call S is P minus 1 over 2, where P is the electron index. So it's the index in which that describes the energy distribution of the power law, which describes the energy distribution of the electrons. So from that, you measure the synchrotron spectrum, you measure the power law index, from that you measure P, the index of the energy distribution, which is exactly what we have here. So it's a way of testing, of measuring, indeed, whether, and indeed we see that the index is between P and 2.2, 2.3, so very close to 2, the value. I see 2 here, but I mean with minus, of course, so minus 2. So very close to the minus 2 value that we obtained in the previous slide, so the theoretical value. So even these mechanisms are very complex, essentially, they are very close to the basic line of reasoning that we just follow. This is just an example of, this is a plot in which I show you for a number of supernovae, and depending on the kind of supernovae, this is the kinetic energy profile as a function of the ejecta of the velocity. So ejected means that, okay, you have an explosion, so you have matter which has been expelled. You have to consider for any given object, matter is not expelled all at the same velocity. We have a distribution of velocity. So these lines essentially tells you the distribution of single objects. So in particular, this line here is telling you, well, it's telling you here you have matter expanding with this is a forward velocity, gamma beta. So with this velocity here, and then some other matter with a velocity here. So you have a distribution. This is faster ejecta, this is slower ejecta. But you see that most of the energy in any case is carried away, is carried forward by the slowest ejecta. So most of the kinetic energy. So that explains why you have a decreasing function. This is a log-log plot. So all these straight lines are power law. And you see also here the index. These are non-relative. So these supernovae here are non-relativistic. So it means that if you take the fastest ejecta of this guy here, it is still non-relativistic, mildly relativistic, because you see you are far below 1. But there are also objects in which you see that this power law is shallower. So it means that, again, also for these guys here, most of the kinetic energy is carried forward by the slowest ejecta. But in proportion, the fastest ejecta now can be mildly relativistic, and in proportion, the fraction of kinetic energy carried forward by the fastest ejecta is less negligible. And the extreme case is due to the gamma ray burst, the blue points. The blue points, you see that again, most of the energy is again carried forward by this the blue square here, so by the slowest ejecta. But if you consider the fastest ejecta, well, first of all, you realize that these are ultra-relativistic. And the second point is that the kinetic energy carried by these guys in proportion is not more so negligible in respect to. So it means that you have a significant fraction of energy in this explosion which is carried forward by ultra-relativistic matter, which is expanding. And indeed, so this is a way of showing you that there is a range, an entire range of non-relativistic and relativistic matter expanding, which so develop non-relativistic up to relativistic shocks. And all this plot is just an example of stellar explosions. So stars, which massive stars, which at the end of their life just go bang, and just the collapse. There is the collapse of the core, and then there's a huge shock wave which just disrupts the star, and in these cases there's also the creation of a relativistic jet which is responsible for this guy. So all this to show you that indeed in nature out there are these objects, and there's also other objects, but this is something in particular close to my field of studies, which are indeed responsible of developing and can really naturally develop shocks of all ranges. So summing up, we've seen that essentially the first order mechanisms that takes place in collision and shocks are the most likely candidate to explain what we see in terms of cosmic rays. Indeed, one of the key ingredients is the magnetic turbulence. So these shocks have to be very efficient in developing magnetic fields due to turbulence across the shock. And also the magnetic field amplification is also something which is a very complex topic, but it is important to explain the energy that we need. And this is a highly non-linear process. So everything non-linear, it means a small change can turn into a big change. So it is very complex to study. And again, here there's a lot of both numerical and theoretical work in this field. So it's a very, and these are just a list of open issues that are, of course, you are not supposed to know, just for your curiosity. Some of the aspects which people are just focusing on just to see. So this is a very, very hot topic and also a very complex one. So this is the main references. I mostly used the Longueur treatment as well as the Vietri. Also, Vietri is very has clear explanations about what happens particularly in the across the shock concerning the particle acceleration. So this is the textbooks I advise you to look at to see what I just explained. If you are curious, again, this is a possibility I offer you. These are reviews in which they essentially move beyond and they explore more in detail a lot of things that I didn't say. So just for your knowledge, your curiosity. So that's all. And so first of all, so do you have any questions?